which I'm gonna do. So our next speaker is Alan Pearl. He is a rising fifth-year astro grad student at the University of Pittsburgh. He loves coding, rock climbing, and making mock universes. He's going to talk about today his research on galaxies and how they interact with the dark matter. Over to you now, Alan.
Okay. Okay, so hey everyone, thanks for that nice introduction, Yasha. She said, I'm a grad student here at Pitt, where I study galaxies and specifically how they're connected to the dark matter, which is in and around them. So I'm going to start by showing probably one of the most famous images in the history of astronomy. This is the Hubble Deep Field. And the story behind this image is that basically this Hubble Space Telescope was, before this point, almost always pointed at a star or a galaxy or something that we knew was there already, and so that we could study it more. But instead of doing that, somebody had the idea to point the telescope at sort of the emptiest, darkest region in space that they could find, and so that's what they did. They pointed the telescope, which was the best, most expensive telescope in use at this time, at this one spot with nothing that we knew of in that spot in the sky for 10 straight days. Not really expecting much at all, but this is what they ended up with, this beautiful image where you can see sort of an endless expanse of distant galaxies of all colors, shapes, and sizes, which is our universe. And astronomers were kind of inspired by this enormous, diverse population of galaxies they didn't know existed before. And a major goal since then has been to sort of make use of this galaxy to study the history of the universe. So here's like what we know now about the history of the universe. First of all, it's 13.8 billion years old. In that time, it's been evolving and a lot has changed. It started out way smaller than it is today, but then we know there was some sort of big bang that caused expansion to start, and it continued expanding, and it's even still expanding today, which basically just means that galaxies on average are slowly getting further and further apart from each other. And if you look at this entire timeline, astronomers are actually able to take images of galaxies at any point in time on this timeline. And this is because we can collect light from distant galaxies that are so far away that the light we're seeing now was emitted billions of years ago. So in other words, the further in the distance we look, the further back in time we're looking to. But there's actually a limit to how far back we can see. So for example, if we point a radio telescope literally anywhere on the sky, we're able to see this afterglow light pattern, which was emitted only a couple 100,000 years after the Big Bang. And before that time, the universe was actually too dense for light to go very far before hitting into something else. And so that was sort of the first time any light was able to be emitted. And we're actually able to see it here on Earth, which I think is pretty cool. And so here's a better view of that afterglow from the Big Bang. This is a full sky image, and it's color-coded based on the intensity of the light, of the radio light. And so the brighter, redder colors means that's an area where there's more light, and the dark blue means there's less light than normal there. So the discovery of this pattern that you're able to see all over the sky is one of the most important discoveries in astronomy, really, because it essentially gives us an initial condition from the furthest point back in time that we can see. And since most of this light was emitted by matter, mostly in the form of hydrogen, the statistical distribution of this light corresponds to the statistical distribution of where that matter was in the early universe. So it's sort of that initial condition I was talking about. And what's even crazier is we can model this light, and we found that the only way that this distribution of light is even possible is if only 15% of all of the matter actually is able to emit this light. So that means all of the hydrogen and other small elements only composes 15% of the universe. And this is kind of confusing because we don't really know about many other types of matter that could account for the other 85%. And so for now, we just call it dark matter, sort of as a term for our ignorance, and because, well, it doesn't interact with light, therefore we can't see it, and so it is dark in a way. But the point is, we know the initial conditions of where all of this matter is located, and from these initial conditions, every single particle of matter is gravitationally attracted to one another, which causes these bright overdensities to grow over time as they accumulate more and more of the surrounding matter. And this is how we study the evolution of large-scale structure, and we're able to actually simulate that very accurately. So this is an example of a simulation where we start from those initial conditions and then just let time evolve and see what happens. So like I said before, the densest clumps just get even denser and more massive as they attract the surrounding dark matter through this really messy merger process. This movie is color-coded by density in a way that the black has very low mass and the orange, the bright orange, has a lot of mass. And so when you see all these little balls of bright orange, that actually represents a lot of dark matter particles that are all sort of stuck together by mutual gravitational force. And we call these clumps dark matter halos. Each of these really bright balls that look like they're all traveling together. And I apologize because not only is halo a jargon term, it's bad jargon. Halos are not actually in the shape of halos. They're just these round clumps of dark matter that are pretty densely concentrated in the center and get more diffuse on the outside. But you can just more or less think of them as spheres, really, not halos. So this is a much bigger dark matter simulation. I drew a little red square around a small part of it so we can zoom into that square. And when you zoom in like this, you can see the individual halos just like in the movie in the last slide. So now we know the dark matter in the universe looks something like this because we just simulated it, but we can't, when we look out into space, this isn't what we see because you can't see dark matter. When you look out into the universe, you see galaxies like that. Galaxies are the only beacons of light in the universe, so that's all we're going to see. But we know that halos and galaxies are connected in a way. Galaxies are also subject to gravity, and so logically, if they started out with approximately the same initial condition and they were subject to approximately all the same forces, they should end up with a sort of pretty similar distribution to the halos. And in fact, we think that every single galaxy forms inside of a dark matter halo. So this is a model, this image, with blue and red dots representing different galaxies that formed inside of the halos in the simulation. And the problem is the physics of galaxy formation is really messy and complicated. And so for the most part, we don't actually simulate that to learn about it. We learn about this process from observational data. And we basically just try to place the galaxies into halos where they fit best. So the study of placing galaxies into halos where they fit best is called the galaxy halo connection. It's basically this bridge that connects simulations and tries to make sense of it at the same time as making sense of all of the observations. And so there are two main ways that we can test if a galaxy fits inside of a type of halo. The first most important thing is to make sure that the abundances of the galaxies and halos match. So for example, in simulations, we see a lot of small halos, and it's more rare to see really, really massive ones. So I drew halos as these orange circles, and the bigger ones are more massive. Similarly with galaxies, we observe a lot of small galaxies, and there's a lot smaller number of the supermassive galaxies. And this kind of makes sense because you would expect galaxies and halos to sort of grow together, and therefore, small galaxies started out living in smaller halos, and over time they grew, and so now big galaxies live in big halos. But abundance matching is sort of a more quantitative way of saying that, and it's a way that you can actually predict how the mass of the galaxy correlates to the mass of the halo. So the other main way to make sure that galaxies fit inside of halos is to quantify a clustering signal using a statistic like the 2-point autocorrelation function, but you don't need to know what that is. It's just some signal that the larger the signal is, the more clustered the data is. And to give you an idea of how this clustering signal works, I plotted a bunch of uniformly sampled random data, and this data is not clustered. Sure, there are some points that randomly end up very close together, but this is how we define our 0 point, essentially, of clustering. Randomly sampled data is defined to have a clustering signal of 0, so we're not going to apply anything for this yet. Next, I'll show you data with a little bit of clustering. So this is a simulation of just the low mass halos, and they're a little bit clustered. You can definitely see that each point preferentially lives near another point. So halos preferentially are going to live near other halos, is what that means. But they're also sort of distributed everywhere. You can't really find too many places where there's no data at all. So next, here's a population of medium mass halos. They're much less likely to be sitting around in these underdense regions where there's nothing else around. They're much more likely to live in the clusters where other more massive halos are clustered. You're starting to see this trend where the higher the mass, the more clustered that data is, and that's a trend that's going to continue. Here's the highest mass halos in orange. They only live in the densest environments, which means they have the highest clustering signal. And I could show you exactly the same thing with low mass, mid mass, and high mass galaxies. And if I did that just right, then they should have a very similar clustering signal to these halos. And this does like a great job of giving us some additional information about the galaxy halo connection, because it's just this extra check that we can do to make sure that the galaxies really do fit well in those halos. So knowing how we learn about the galaxy halo connection, now I'm going to show you what we know in cartoon form. So first, let's line up all of the halos from lowest mass on the left to highest mass on the right. So remember from the abundance matching slide, there are more low mass halos than there are high mass halos. That's sort of intentional. So now we're going to place a single galaxy inside of each halo. And the more massive the halo, the more massive the galaxy that is placed inside of it. So this isn't a perfect correlation, but it's pretty good for the most part. And now I'm going to add an element that I haven't really talked about before. So these really big halos, they only got that big because they have been accumulating matter from all around them. And during that process of accumulating matter, that matter includes other halos. They actually sort of, gobble up other halos that end up orbiting around them. And sometimes those halos bring in galaxies with them because halos tend to host galaxies inside of them. So we call those galaxies that end up orbiting around other galaxies satellite galaxies. And so I put in a bunch of satellite galaxies in the cartoon now. The important thing to note here is that more massive halos have accumulated more mass, and therefore they've accumulated more satellite galaxies, so they have more satellite galaxies. So now we're basically done. If we remember where all of the halos were located in the simulation, we can kind of put them back there with their galaxies that are living inside of the halo now, and we have ourselves a mock universe. And from that mock universe, we can make mock observations. But some of these galaxies are just too small or too dim for us to see. So we're going to throw those out. So then you're left with something like this. And we have sort of all the same trends as before, but the low mass halos just don't have any galaxies at all. And when we match this kind of a picture to real surveys, we find that it works very well with both abundance matching and the clustering signals. And we can even take a few steps further. For example, if you broke up the galaxies into whether they emit more red light than blue light, or vice versa, you would find that the red galaxies are more likely to live in higher mass halos, and the bluer galaxies which are the ones actively forming new stars, tend to live in the lower mass halos. And this is partially because they tend to be lower mass themselves, but for now we're just going to stick with the story that it's this correlation with the halo. And so we're always looking for additional ways to make this picture more and more accurate, more correlations with properties. And just as one quick example, you can look at more halo properties like the rate at which the halo is accumulating matter. And in our models, we're actually seeing a small preference for bluer galaxies tending to live in more rapidly accumulating halos, and vice versa, red galaxies living in older, less rapidly accumulating halos. But the evidence isn't super strong for this. Take that with a grain of salt. We need a lot more observational data before we can say anything for sure on that. And so now, just to summarize, the most important part of the galaxy halo connection for us to really get right is that correlation I was talking about between the mass of the galaxy and the mass of the halo that it lives in. It's super important to know the mass of the halo that a galaxy lives in because that affects so many aspects of how the galaxy forms. And galaxy formation is a really hot research topic in astronomy right now, so a lot of people are really interested in this. And so a lot of people, me included, have put a lot of effort into being able to measure this trend that we see on this plot. So in this plot, I have multiple lines and colored points, and essentially they all just represent different studies that have used different telescopes and instruments, and some of the points are actually future telescopes and instruments that I've been looking into what constraints they're going to place on this connection. And so, yeah, that's just sort of an exciting thing that we're looking into. And that's been a big part of my research here at Pitt. And so I just want to conclude now by showing you some pictures of these, huge telescopes and observational instruments that are going to continue to pave the way for us to expand our knowledge of the galaxy halo connection. So in the coming years, these telescopes are going to take a lot of data from galaxies in the distant universe. We're going to have sample sizes that we've never seen before from galaxies so far away, and therefore so far in the past. And this should really break down some doors for understanding how the galaxy halo connection has evolved over the history of the universe. Yeah, we're all super excited to see whatever we end up discovering from these new instruments. And so thank you for listening to me talk about space stuff. I can now take any questions.
That was amazing, Alan. Thank you. I'm gonna open the ramp for people to ask any questions. Just do the raise hand feature on Zoom or just unmute yourself and ask any questions. I do see one question in the Slido app. So why is the question is the galaxy halo connection today similar to what it was in the past?
Yes, essentially, or so we think. I guess what I should really say is we don't exactly know the answer to that question because 99% of what we know about the galaxy halo connection is measured at like low redshifts. And so this plot is trying to show, sorry, I shouldn't say the word redshifts. I should say ages of the universe. And so most of this data is showing data that's taken from very nearby measurements, which means like current day universe. But as you move to earlier and earlier universe, it could potentially change, but most of our assumptions are that it doesn't change super heavily, in that both the galaxies and halos decrease in their mass because they were just forming and they start out smaller than they end, but they sort of both go down this trend together in a way that this sort of stays constant, and that's what we're assuming for now. But definitely is subject to change.
Makes sense. Very cool. Do people have any questions? If not, I'm gonna just put the feedback form for our speaker 2 here in the chat box. Please take a couple minutes to fill that. That would be really helpful for future talks of our speakers. Thank you so much for showing up, everybody, and being a part of our No Jargon Talks series. It was amazing to have you all here. I hope speakers also enjoyed giving the talk. We all definitely enjoyed. I know not everybody is showing their video, but I'm pretty sure they took something from the stuff. Yeah, very cool. Thank you for being a part of the No Jargon series session 2, guys. See you all in session 3 then.
Thanks. Bye.
Bye, everyone.
Bye. Thank you.
Thank you.